Hello, everyone. Good afternoon, and welcome to today's expert session, which is a joint session with BASF and HP 3D printing and digital manufacturing. The session is about materials innovation and advanced applications, and we will be having a panel, and we will be talking about especially polypropylene and TPU materials. Today on the panel with me, we have María Tauler, Materials Product Manager and HP 3D Printing. Also Julia Roth, who is Technical Sales Manager at the BASF Forward AM. And as a special guest, we have Andreas Knöchel from Oechsler, who will be showing his perspective on actual use cases with these two materials. So Maria, Julia, and Andreas, welcome to this session. And Maria, if you want to start.
Yeah, thank you. So today, the three companies, we will be covering, first of all, the strategic alliance that we have built, and a little bit why HP, BASF, and Oechsler together. And we will then follow with the TPU material that we introduced almost 2 years ago already. And then we will follow with the polypropylene material, also giving an overview on the applications that this material will enable. And we will finish with the use cases for both materials. At Oechsler, we'll explain their experience because they are already working with these two materials, so they will be able to explain their real use cases. So let's just start on the strategic alliance. And today we wanted to share a little bit why these three companies together and what will bring. So the three companies have a strong strategic alignment. They share the same vision to disrupt the industry, and they share the same application focus, especially on medical, on consumer goods, in industrial, in automotive, and also have same risk tolerance and significant investment levels on a long period of time. So these are one of the key points. Also, the three companies are industry leaders in their field. BASF on the material field, HP on the additive manufacturing processes and printing, and Oechsler in the design and engineering and also additive manufacturing and manufacturing factory operations. The three companies also complement each other to offer an end-to-end view. So each of the partners will bring a different step of the end-to-end process. And all together, what we will be doing is delivering to the end customer the full solution. The strategic alliance of the three companies is extremely powerful and a catalyst solely capable to disrupt traditional industries, which may be prone to disruption. So with this new strategic alliance, we are enabling a shared commitment to sustainable production and acceleration of a more circular and low carbon economy. With this, we will now move to the TPU material that BASF have developed to work with our 5200 series printer. So what this material will bring to our HP solution, it's a strong and flexible elastomeric material. It especially will enable parts that require shock absorption and that require also energy return and resistance to fatigue. Also, another key point that BASF will bring and that Julia will explain in more detail is the ultrasim for design optimization, that especially for this type of parts that require lattices to optimize the performance, this ultrasim solution will be a key thing. Another key value of this material is the look and feel. A lot of elastomerics materials in the market today have very rough surfaces, and the look and feel, the level of detailing is not very good. So with this TPU together with BASF, we have accomplished to have a very high level of detail, and the surface quality is really, really good. And moreover, it's also very easy to finish, and you can smooth the surface, you can do some coatings that BASF has developed, so the solutions are very wide. And then the third pillar is in the productivity, and this is thanks to the 5200 series printer, that it has a very high productivity, and also the printer itself has we have optimized this printer to have a lot of a high process stability. So from CAD2 files, you can send the files to the printer, print them, and clean them in less than 24 hours. So it's the fastest time to part in our printer today. And all this also with a very important fact that it's a highly reusable powder, up to 80% of reusability ratio, that this will also have a very cost competitive solution. Now I will pass it to Julia, and she will explain the applications that we are enabling with this new material.
Yeah, Thank you very much, Maria, for guiding us through the USPs of our ultra-thin TPU-01 material. To make it more tangible for you, I will now talk about the target application suitable for this material. So as you can see on this slide, we have identified 3 main segments. The first one is automotive. Example parts are soft jigs and fixtures for scratch-sensitive parts like grippers or human protective parts for manufacturing lines, but also air ducts, pipes, and interior components. In collaboration with both HP and Oechsler, we have specifically been looking into lattice structures printed in TPU that can be used for automotive applications where cushioning is of importance, for example, seats, but also headrests that you can see on the slide. Secondly, we see a major application area within consumer goods. This can be anything from footwear to sports equipment, where we are using the benefits of AM to customize, for example, soles or inserts. And again, lattice structures can be very suitable for such applications in the consumer goods industry. For example, the shown helmet, the lattice parts can here improve protection, enhance the comfort and breathability, and at the same time reduce the weight. Last but not least, we have identified TPU applications in the wide field of the industrial sector. Examples for this are components of manufacturing line equipment and robots. Any kind of tubes and pipes with customized flexible shapes for easier assemblies, as well as electronic equipment components like soft and flexible housings. To enable your application, BASF offers a broad portfolio of services besides the pure material supply for an end-to-end support. This includes support in everything that happens before the printing as well as after the print job has been done. On the left side, you can see our BASF UltraSim simulation software. The software is already well known for injection molding applications, but it can also support with the transfer from conventional manufacturing to additive manufacturing. By design and simulation, the component behavior can be adjusted almost at will. For most applications, such as the one that Andreas will be showing later, a part simulation prior to the printing is crucial for a fully functional part that meets all requirements. On the right side of the slide, you can see our post-processing capabilities because our solution does not stop with the printed part. For some of the applications we are developing together with HP and Oechsler, an appealing touch and feel is very important. By using chemical etching, we can achieve perfectly smooth surfaces that are desired for many applications, especially if they are visible. And our ultra-cured flexible coating does not only beautify your parts, but it can also improve specific performance aspects, such as resistance against chemicals and also abrasion, dirt repellency, and also UV protection.
Thank you, Julia. Yes, so we introduced this polypropylene material more than 6 months ago already, and this is a very exciting material for us. Polypropylene material in injection molding is a very popular material, so we having now this in 3D printing, it's very, very exciting. What this material will bring, first of all, is that it's the most important thing is that it's a real PP, a genuine PP material, and this will help a lot accelerate the design process for a lot of companies that can now prototype and do the final production with the same material. They could use the 3D printing technologies to prototype and then do the injection molding part with injection molding once the application has a scale, but having this same chemistry will really help customers to start adopting this new technology. This material will also bring excellent chemical resistance, and this is also thanks that it's a real PP material. So we have done several testing that Julia will share, but we've seen that the results are very, very similar to any polypropylene that you would find in injection molding. Another key value that this material will bring in additive manufacturing is the welding capabilities. Now you will be able to weld 3D printed parts with injection molding parts, and before that was very difficult because to be able to weld PA12 with injection molding PP, it's impossible. So you can now do it with PP in both sides, and the welding is very easy. You can use the same processes that you are currently using with your other PPs. And the third key property of this material is the low moisture absorption, that this will also be a key enabler for applications that are in contact with water, fluid systems, and all these type of parts. And then the third pillar is on the cost. As you know, an injection molding PP is one of the lower cost material. And in 3D printing, it's the same. It's one of the lowest. It's the lowest cost material that we have today in our HP portfolio, and not only because of the material price, but also this material is up to 100% reusable. So this will really help decrease the cost compared to the current solutions that there are today in the market. So which are the applications that this material will enable? Here you can see the main markets that we are targeting with the type of parts. In automotive, it's one of the big markets. In injection molding and traditional methods, they use a lot this material. So here what we are seeing a lot is a lot of prototyping parts, interior parts, welded parts, fluid systems, HVAC systems, all this prototyping to be able to do it with the same PP material base has a lot of value. And not only that, but also you can start doing the ramp-up production for lower volumes with the additive manufacturing solutions. On industrial, we also see key benefits for this material. All the machinery parts, all the tubes and piping. Here, in a lot of cases, these parts that you can see in the images are in contact with water or with chemicals. So you really need PP material for these parts. You would not be able to do it with other materials. Then on consumer goods, there are also two different markets, subsegments that are really interesting for polypropylene material. The household appliances, in traditional also this subsegment is working a lot with polypropylene material. So to be able now also to do the same prototype and do the first ramp-ups of production with this material will also be a key thing for these markets. And then also on the cosmetics applications, like the parts that you are seeing in this image, polypropylene material can also bring a lot of value because it's also a lower cost solution that can help to open this market for the test markets. And then the fourth is on the medical. And here we are seeing a lot of traction from the orthotics customers. Here think that all these orthotic customers, they are usually used to work with polypropylene material. So to be able to use the same material, but now with a new technology, it's much easier to do this change. Also, one of the key properties that this material will bring is that once the part is printed, you can heat it to be able to adapt it to the shape of the patient. And this is a key thing that the doctors are always suffering when you do it with other materials, that you cannot do this heating, and thus you would need to reprint the part again. So with this polypropylene material, you can do this, that traditional customers are usually, that orthotic customers are usually doing with traditional methods. And now you can do the same with this PP material. So what we wanted to do now is give a little bit more detail on the chemical resistance and the welding capabilities of the material, because these are two of the key properties that this material will have. So now Julia will explain you more about that.
Exactly. So yeah, thank you again, Maria. So as Maria was mentioning, the two of the main arguments for using PP are the chemical resistance and the welding capabilities. We have tested parts printed in PP by exposing them to various chemicals, such as water, alcohol, but also some acids and other chemicals that are commonly used in automotive, industrial, or consumer goods industries. As you might be able to see in the picture at the bottom left, the tested parts have shown little or even no change in dimension after doing the test within those chemicals. Also, the mechanical, such as at break, remained mostly unchanged. On the other side, and besides the chemical resistance, our polypropylene material shows excellent welding capabilities. On the slide, you can see a list of some of the welding techniques that we have successfully tested for PP parts. This allows one to join parts that are still printed via injection molding with 3D printed parts in PP, and that can therefore save a lot of time, money, and that in various applications. Also, when it comes to simulation and post-processing, we offer many solutions such as the coating for our polypropylene as well.
Thank you, Julia, for the details on the polypropylene material technical side. We will now move to the Oechsler part, where we have Andreas. He is the head of program management for additive manufacturing, and today he will be explaining us some of the use cases that they've been developing for the TPU and the PP material. So Andreas, all yours.
Thanks a lot, and also hello from my side to all of you. First of all, I would like to have a few words on the design capabilities. So on Oechsler side, we are using market available design software, but we are adding two special Oechsler facts. One is our in-house developed algorithm on lattice design, and the second is all our production data from the past. Having both of these in hand, we do have the capability to design the lattice geometry for our parts, the inner volume as well as the boundary lattice, in a way that we do have a very high hit ratio when it comes to prototype, meaning we do not need to run through a lot of loops and print a couple of times. We do achieve the specification already with the first print. Now I would like to show you some of our use cases we do already have in the field or working on it. First one is the seating made out of the TPU material, also here based on the lattice design. Why seating? That's one of the biggest questions everyone is asking us. By using lattice design for 3D printed cushioning elements, we do have a huge benefit to the customer. We bring a high comfort to the product. High comfort does mean we can add, for example, multiple hardness zones within one part. For example, on a car seat, backrest can be way different as the seating area, or even within a tiny spot. Just having your shoulders hitting the comfort element, you can have it softer or harder depending on your needs. On top of that, on the comfort elements, we definitely also see that we can achieve less weight in the component compared to regular foam. And on top of that, less space. Why less space? For example, regular seating, if you need around 10 centimeters foam cushioning, we can achieve the same or even better comfort zone and hardness areas by only having 4 to 5 centimeters. So almost 50% can be saved in that way. And last but not least, if needed, we can achieve very easily an individualization on the seating, that we can comfort heavier to lightweight persons sitting on the same looking seat. What you see on the left pictures, one is a model, one is a real part. So seating, what you see is our showcase model, where we can demonstrate pretty easily the capabilities of lattice. So you see a lot of lattice elements, seating, cushioning, headrests. This is already achieved also in serial available car seats. What you see on the right side, the two pictures, the lower picture is the real part. It is a motorcycle seat for an available motorcycle. On the top picture, you see the same part in the simulation and in the development stage. You do see different hardnesses going all over the surface without having any restrictions, starting in the middle from very soft to the outer boundary where it ends up in a hard zone. There are no steps at all. So you as a customer would not feel any steps. It is a very smooth transition from soft to hard. And all of the two versions, as I mentioned, we are really going for production in a bigger way. In the second use case, what do you see? We call it RoboSkin. Also made out of TPU and with a finish on the already explained post-processing. What is the RoboSkin? The RoboSkin is a passive protection device for our collaborative robots. Collaborative robots, while still needing something to protect. As of now, if you use a collaborative robot, you still have to go pretty slow when it comes into the special areas where the robot interacts with the human being or the worker. To overcome this limitation, you can add a cushioning that the speed, for example, can be increased. That's a protective function. On top of that, if you put such a protective function to your hard metal skin, you cannot just do it by foam. Why not? Because the robot would overheat very, very fast. You can imagine with our lattice structure, which is an open mesh structure, it is permeable, meaning the heat can go out and you don't have an overheating. not only looking into the robot, you also do have the unique end-of-arm tools, which could be different from application to application. By using here the technology of 3D printing with our lattice structure and the smooth structure, we are very flexible to adapt the RoboSkin to a lot of different tools, meaning the geometry can be different either from tool to tool or from customer to customer, which is not an issue. Simplifying, yes, also that system is simplifying because you do not need to add any sensors. Sure, you could achieve the same function by adding sensors, but it is way more cost intensive. Plus, it's not as simple to set up as you would just add a skin. As well as on the lightweight function, you also have space saving, meaning the thickness is very minimal. You do not add a lot of material to your robot. And as I mentioned, the lightweight, you don't have any impact on the payload. Yes, we are adding a couple of grams, but the weight is so low that the robot can almost use its full payload. And last but not least, it's easy to mount. In case you need to take it off, you can do it. We bring in functions that you can snap or unsnap it without the need of any tools. It can be done really by the regular workers. You do not need special technicians. And as mentioned, also that one we are already using. It is in the market. The first RoboSkin itself we are using in this case on a KUKA. It's the EVA 14. Okay, coming to the third use case, we are coming to the polypropylene technical parts. What you see here are some manifolds, some piping, including a housing. By using the PP, the polypropylene material, on the one hand, we are using the 3D technology to make the impossible design possible, especially in a scaled mass production. But when it comes down to fluid pipings, for example, and what you see on the left side, we definitely have the big advantage of the chemical resistance against the fluids, against the solvents, for example. But also, even if there is on some parts the possibility to produce out of one piece, especially on housing, like you see on the lower right picture, the housing still does have a cover. We can use the very good advantage for the welding capabilities, meaning even there, without using any special adhesives or even screws, we can mount the two components together, which was, as mentioned up front already, not possible until now. By going for the PP, which does have almost the same technical properties like regular polypropylene, we definitely are also in the position to skip for our customers the tool waiting time. If you go, for example, for simpler parts, meaning by already being able to produce high quality grade in polypropylene 3D printed parts, we can print, for example, the first 6 months the parts directly out of the HP printer and only switch to the simplest geometry parts to injection molding afterwards after 6, 7, 8 months. Sure, here we definitely then have a big time advantage for our customers, and they don't need to wait for parts for serial production. And now, as I showed you a couple of use cases we are really dealing all day long with, I want to give you a short outlook to the future. For us at Oechsler, we're working together with HP and BASF quite a long time. And for us, 3D printing is really a mass production and not in the future. Just have a look at our 2020 numbers. We produced more than 2.2 million pieces already, sure, with quite a lot of technologies, but definitely we will ramp up the next couple of years and scale the TPU as well as the PP business with HP and BASF. We have right now 200 printers already in our fleet, and we are ramping up the next couple of years for more than double of that.
Thank you, Andreas, for the explanation on the real cases with both TPU and BASF material, and also thanks, Julia, for everything that you shared from BASF point of view. For those of you listening, thank you for attending our session, and please don't hesitate to contact any of us at the Formnext Connect platform. Thank you very much.